So we are going to start. I guess you can hear me from outside. Yes?
Yes.
Okay, thank you. Well, as always, we will be recording the session. So if someone doesn't want to appear, just don't talk, don't do nothing. Okay. Good morning, everybody. Thank you for coming to this second session of the reading group. In the first session, David was talking us about all the background that is needed in order to start understanding the inner workings of today's famous large language models. And in this session, my goal is to shed some light on the basic computational algorithm of large language models, which is the transformers. I'd like to start with a slide about what I think are the key methodological innovations that have led to the deep learning revolution. I'm just going to talk about methodological innovations, but keep in mind that the main responsible of this revolution is data availability. We have a lot of data available for us nowadays, and the democratization of computational resources, like computing in a massive system with a lot of GPUs nowadays is very easy, like any can do it. So I would like to highlight that most deep learning algorithms nowadays aim at learning a parametric function. The goal is always to learn a parametric function, f of theta, that approximates a target function, f, from a set of input output pairs. These are what are called the training data. And this problem is essentially solved by finding these parameters, the parameters that minimize a loss function, a certain loss function that depends on the training data, and some measures the discrepancy between f theta and f. Okay, this is very. This statement is simple, but I want to make it clear because we have a very inhomogeneous audience. So the three main things from a theoretical or methodological perspective that has helped in solving these problems, in my opinion, are these three things. First one is a stochastic gradient descent, which is a technique to solve this optimization problem, right? That enable us to work in the regime in which n, the number of data points, is very large. Okay, like in each iteration of this problem, we would need to load in memory the whole data set. N is very large, like imagine all the tests with which GPT has been trained. That's not possible because we cannot load all this data into memory. But a stochastic gradient descent, which is a technique, by the way, invented in the 50s, in the stochastic approximation literature, enable us to work with batches, with little amounts of data, and still be able to solve this optimization problem. The second technique is automatic differentiation, which is a technique in order to compute the gradients of this loss function that we need in every iteration of the optimization algorithm, right? With this technique, for almost any program, any set of computations that given an input computes an output, enables to compute the gradient with a complexity very similar to the evaluation of a function. So computing the gradient has almost the same complexity as evaluating the function. It's almost as fast as evaluating the function. And this is the second key development. These two has to do with the training process, with the optimization, solving the optimization. The third one is the introduction of very innovative architectures. Architectures are nothing else than shapes of these parametric functions, f of theta. We have a lot of architectures now. Some of them has nice theoretical properties like the multilayer perceptrons, and and others work very nicely when the domain of a function is of a particular form. Like for instance, transformers, which is what we are gonna see today, they work very nicely when the domain is a set of sequences, as we will see, okay? Sequence data could be, for instance, text. So what is the purpose of this talk? Quoting Feynman, he used to say that what I cannot create, I do not understand. And I strongly believe that if he was alive, he would say nowadays, what I cannot code, I do not understand. So what I want to do in this session is to first understand the inner workings of transformers, trying to code them. Okay, so I'm gonna go step by step on how would you code the transformers. I have some code. We are not gonna do everything, like I've done most of the work before, but I think that with this talk and the code that I gave you, I think that you would be able to reproduce and understand how transformers work. Okay. It's important. We are not going to talk about training. We are not going to talk about once we define the parametric function, how to optimize it with respect to the parameters. And the reason is that this is rather standard. Okay. This is always done by a stochastic gradient descent. And in most machine learning frameworks, this is just like 2 lines of code, and it's very easy, as we will see. I will be talking mostly about architecture, about the shape of this f of theta. And the way I think is easier, I have included along the presentation these things highlighted in yellow, which are code pointers. I'm going to be explaining parts of the architecture, and then after every part, there is going to be a pointer to the code. If you go to the particular file, for instance, this would be a code pointer to example.py, and you search for code pointer, and there's going to be a number here, you will arrive to the chunk of code that refers to the theory that I just explained, okay? And all the code is available in this link, which is a link to the repo, and it's also in the website. Okay. So let's start. What is a transformer? A transformer is a particular parametric function, f of theta, which is specifically designed to work with sequences represented as matrices. Okay, a sequence is a text, for instance, a tweet, or could be part of a book. That's a sequence, and we're going to learn how to represent that sequence as a matrix. And these are functions that work particularly well with these types of data. Sequences in which parts of the sequence affects other parts of the sequence or are relevant to other parts of the sequence. Theta are the parameters of this function, and they are learned from a lot of training data. We have a lot of training data in the shape of tests or sequences, and we are going to find the optimal zetas. And all my talk is going to be about what is the shape of this function. How does this function look like? Take into account that this function has a lot of parameters in general that has to be learned. And just to give you an example, GPT-3 has 175 American billion parameters, which is a lot. So we are solving an optimization problem over a huge space. Let's introduce first some notation. By the way, if there is any question during the talk, let me know, because otherwise could be, and there's a lot of information. We're going to work with a vocabulary, and this is nothing else but a finite set, which is identified with natural numbers, okay? My vocabulary could be words, and I give to every word a number between 1 and the length of the vocabulary, or could be subwords, or could be even characters, okay? No matter what is our vocabulary, letters, words of subwords, we will refer to them as tokens, okay? My input data is a set of sequences, and a sequence that I denote as X is a sequence of tokens from 1 to capital N, okay? And these belong to the set of possible sequences of length N created out of our vocabulary. And in addition, L max is going to be the maximum length of a sequence. I will be able to work with sequences up to a certain max length that is defined by the user. So we assume that we have training data, and the working assumption of transformers or machine learning in general is that our data is assumed to be a set of independent and identically distributed sequences that comes from a certain probability distribution. For instance, a collection of independent articles. If we have a sequence that is above, that has length greater than the maximum length, we are going to divide it in chunks, nothing else. Okay, so we are guaranteed that every sequence has at maximum this length. And details about the, yeah. Yeah, that's a problem, but it's always assumed that is independent. Okay. And the details about the particular shape of the data depends on the task that we are facing. And I'm going to introduce the three main tasks that are solved with transformers. First of all, is sequence modeling. Here, we assume that we have a set of n data sequences. Okay, each of them is a sequence, and is assumed to be an independent and identically distributed sample from a given distribution P over the set of sequences. And the goal here is to learn an estimator P of this P of X, or at least maybe not learn this probability, but at least be able to sample from this probability. This is essentially what ChatGPT does. Samples from the set of sequences, gives you new sequences. To solve this P of X is usually decomposed using the rule of the chain rule of probability, and is divided in elements which are the probability of a token given the preceding tokens. And the goal is to learn the distribution over a single token given the preceding tokens. What ChatGPT is doing inside is like we give a text and it's making a prediction of the next token given the prompt that we have made. Once it has this new token, it's introduced to the sequence and learns to sample the next token of the sequence, and so on and so forth. This task in general is called language modeling. Another task is sequence-to-sequence prediction, and this is the original task in which the attention mechanism that we will see, the transformer, was introduced to solve this task. Here we have pairs of sequences. Our data are pairs of sequences from a given probability distribution over this space, and our goal is to learn an estimate of P of set, P of a sequence, the probability of a sequence given the input sequence. This is also decomposed using the chain rule over set. And the paradigmatic example in this is machine translation. Okay, we give a sentence X in Spanish, and we want a sentence Z in Galician. Okay. Between this one and the previous one. Yeah, here we just have a sequence. Okay, so the goal is to predict, to generate new sequences. Here, we want to generate new sequences, but conditioning on an input sequence, which is a sequence in another language, for instance. So in the first one, in here, we are conditioning on some information. Yeah. No, yeah, definitely. And you can work with, I mean, if you work with this conditioned on a prompt, is the same, is sequence to sequence as well. Yeah. But here, the difference is that here, without an input, you can generate tests. Start generating. The last one is sequence classification. Here we have a set of sequences, and each of them has a class. Okay, a class which takes values in a finite set. For instance, you have tweets or reviews, and for every review, you have whether the review is positive or negative. Okay, and these are assumed to be IID samples from a given distribution over sequences and classes. And the goal here is to learn the conditional distribution of the class given the input sequence. It's sentiment analysis. Okay, this is the problem that we are going to solve today. Okay, so once we define our task, the goal is to learn a vector representation of the sequence which is useful for the downstream tasks. So our goal, the goal of transformers, is to convert input sequences into a vector representation, into a vector in a certain dimensional space that will be useful for whatever task we have in hand, okay? So the transformer will learn a vector representation of each token in the sequence. The first thing is to break our sequence into tokens, into vocabulary elements. And there are several ways of doing this. This is called tokenization, okay? Breaking a sequence, a text, into small parts. For instance, if you take this example, Leon is the best city in Spain, and you take the vocabulary to be the set of characters in a given alphabet, the previous example will be tokenized as L, E, O, N, and so on, okay? This is good because the vocabulary is not very large, it's manageable, but requires longer sequences, okay? The sequences are gonna be very long. In the other side, there is word level tokenization, in which V is taken to be the set of words in a language, in English, for instance. In the previous example, the sequence tokenized would be the first word, Leon, is, and so on, okay? This requires very large vocabulary, okay? And has a problem that cannot deal with the new words at text time, okay? What is done nowadays is something in the middle. It's what is called subword level tokenization, where V, the vocabulary, is a set of subwords. Could be short words, could be 3 letters, something like that. Is the most utilized nowadays, and for instance, GPT-3 uses subword level tokenization and has in total 50,000 subwords. So everything that generates is composed out of 50,000 subwords. Okay, so once we choose a tokenization strategy, what we have to do is to assign to every element in the vocabulary, to every word, for instance, a natural number, an index, okay? And there are 5 special tokens that are added to the vocabulary. 5, and sometimes it's less than 5. But in addition to the words, we add a special token that is called pad. It's called a padding token, which is used to make all the sequences be of the maximum length. So if a sequence the maximum length is 15, and our sequence has 10 tokens, we add 5 pad tokens, okay? So every sequence is gonna be of the same length. BOS, EOS are the beginning, indicate the beginning of a sequence and the end of a sequence. Are special tokens to know when the sequence is beginning and when the sequence is ending. Is a token referring to an unknown token. If something is not in our vocabulary, we will assign the unknown token. And finally, mask is the mask token, which is used for certain prediction tasks, in which the goal is to mask part of the sentence of the sequence and make predictions over that part. So a piece of text is represented, yeah.
You're not great part.
Exactly, that's the difference. So a piece of text is represented then as a sequence of integers, right? Which is preceded by this BOS token, and after, at the end, has the EOS token. And as I said, if the text is smaller than Lmax, is padded until this longitude with this token. If the text is longer than Lmax, it's broken into chunks. It's because you need to, for instance, if you imagine when you are generating a new sentence, once the model is trained, you want to know when are you ending the sentence. And when are you ending implies making that the prediction of the next token is going to be EOS. Once you find an EOS, you stop generating. Okay. Yeah, and for simplicity, I will use capital N to refer to the length of the sequences. As I told you now, all the sequences are the same length, and it's length N, capital N. Okay, so there is the first. I'm going to just show you this one in order for you to know how to locate. Go to main here. You will find the code pointer 1, okay? Here is the part of the code let me run this thing. Well, here I'm just importing the main libraries that I will be using. And here I'm defining a set of parameters, okay? The max length, I'm choosing max length 512. And what I'm doing in this example are movie reviews in Film Affinity. What I'm doing is I'm cutting the length to be 512. I'm choosing the 512 first words. The tokenization is done here, okay? You have an example of data. For instance, this is the data with a label. Label 1 means negative, is a negative review, and this is the text of a review, okay? And here in the preprocessing, I'm choosing a tokenizer, which is basic English. This is a tokenizer in which every element is a word in English, okay? And I'm building a set of tokens, okay? Here, the vocabulary size is 100K, more or less. And you can choose this. This is sequence to index and index to sequence. You can create those dictionaries out of the vocabulary that you have chosen in this chunk of code. And for instance, if you take index to sequence of the number 100 is the word made. This means that word made is assigned with the number, with the integer 100, okay? And well, here I'm doing some preprocessing, which I mean, it's nothing very crazy, but I am assigning to every token a word, a position in the dictionary. But before assigning that, I'm making that the token be lowercase. So this is insensitive to lowercase, uppercase letters. Then I will divide my sequence in batches, okay? You cannot process the whole data in every iteration, but you have to process a chunk of data, a set of sequences. That's called a batch. And I'm creating the necessary elements for that. And for instance, here you have a sample of a batch, okay? Each of these elements, okay, is a sequence of words. This is the index of the word. And as you see, every sequence ends with ones. Ones is the padding token. I assign number 1. Yeah. Yeah, at the end of the sequence. Yes. Okay, so each of these is a sequence represented as a set of numbers. Okay, so this is, and here is where I am selecting the maximum length of a sequence that is going to be 512 for this experiment. I have 25,000 sequences in training and 25,000 in test. Let's go back to here. So once we have represented the data as sequences of integers, let's go to each of the steps of the transformers layer. And there are 4. There is a token embedding, positional embedding, transformer block, and the output layer. And I will go through each of them. What is token embedding? The first task that we need to do is to convert each sequence. Now a sequence is a set of integers into a matrix of token embeddings, okay? A token embedding it maps a vocabulary element, an index, into a vector in a certain dimensional space, okay? This is called the inner dimension of the transformer. That is something that we choose, capital D, okay? So sequences of tokens, then, as each token in the sequence is represented by a vector RT in RT, the sequence of tokens is represented by a matrix of dimensions D times N, capital N, which is the length of the sequence. And these parameters can be either fixed or learned. This embedding can be fixed or learned. In this case, it's learned, and in GPT-3, for instance, is learned as well. So we have a matrix of parameters, okay, W, that belongs to this space here, okay, to the space of capital D and the number of elements in the sequence. And all these parameters are going to be optimized, are initialized at random, and then are going to be optimized for the task that we are wanting to solve. All these are parameters that are learned. And this is huge already. Like it's capital D, which could be maybe 1,000 times the number of elements in the vocabulary that in ChatGPT was 50,000, okay? And in my case, it's even more. It's like 100,000, I think, is the vocabulary. Positional embedding. This is one of the most surprising things about the transformers, in my opinion. So what we are going to do, the architecture that we are going to develop, except for this space, is going to be permutation equivariant. That means that if we take a sequence and we permute two tokens, we permute the order of two words, okay? We are going to get the same representation, but also permute it in a few positions. And we don't want this in general because language is not invariant against permutations, right? Madrid is in Spain, it's not the same as Spain is in Madrid. Okay. So the way to solve this is incredibly simple. We are gonna create positional embeddings, which maps positions into vectors, okay? So what we are gonna do is we are gonna take a sequence, which could be 13, 10, 12, the words. We're gonna convert this sequence into the order, which is first, second, third, 1, 2, 3. And we are going to map 1 into a given vector in dimension RT, 2 into another vector in dimension RT, and so on. And these parameters, again, are going to be trainable, are going to be learned. So we assign a vector to every position. Before we were assigning a vector to every word, now a vector to every position. And once we have this, we have the vector representing the word, which is this one, the token embedding, the vector representing the position, and we add them. We sum them, nothing else. Okay. So this somehow is capturing what is the influence to have word Madrid in position 3. Okay. And this is going to be the initial representation of a sequence for the transformer. So a sequence is going to be represented as a matrix of D rows and N columns. D, the inner dimension of the tokens, and N, the length of the sequence. Yeah, naively. And I said that it's surprising because just this thing solves the permutation equivariant problem, and it works really nicely. But as most of the things here, there is almost zero theoretical support for this. It's just trial and error, and that's the reality. Yeah, but whatever it is learned with enough data is learned, which is, I mean, would be very interesting to understand why this simple thing works, but I don't think anybody understands, at least for the moment. It's just that they tried and it worked. And even like, for instance, in the attention paper, these positional embeddings were not learned, were fixed, were functions, were trigonometric functions, sine and cosine functions. So fixed and they were working. But nowadays, GPT, for instance, is working with learnable embeddings. Okay. Well, there is here another code pointer that I will go very quickly. This is in transformers.py. So if you go here, this is where I defined the transformers block. Okay. And you can find here the code pointer. So all I'm doing is I'm defining a token embedding, which is nothing else but a linear transformation. And this is defined this way in PyTorch. It's a linear transformation that converts tokens into matrices. And these parameters are length. And here I'm sending the token. This is the forward parse where I introduce a sequence or a batch of sequences in this case and computes the output. And the first thing, here the sequence is represented as a sequence of integers. The first thing is to represent it as a matrix. For the position, I'm sending just this thing, which is indicating the position of every word in the matrix, in the sequence. And I'm converting this to a matrix, and I'm just summing these two things. And here I'm introducing a bit of regularization, but this is not very relevant for the purpose of the talk. The representation is just the matrix corresponding Okay. Mhm. Okay. Thank you. Oh, it's not working. I have to use this because it's taking the audio, the audio for the Zoom. Otherwise, I wouldn't. Okay. So now we have each sequence represented as a matrix. Okay, and I'm going to label it as X0. It's the sequence at the entrance at the beginning of the transformers block. And the transformers is a set of operations that convert this sequence X into a sequence of the same dimension, into a matrix of the same dimension, after applying a few operations. And they generate a new representation of the input sequence by applying a series of transformers blocks. So we are going to see what is inside these transformers blocks. And there are two main stages. There is a self-attention, something that is called self-attentions across the sequence, in which the representation of each token is a vector, is modified, is refined, considering other tokens in the sequence. How much the word I affects the word in position J, okay? So this is set to ask to act vertically in this matrix representation that I showed. And then there is a multi-layer perceptron across features in which each feature is representation is refined independently from others without considering the other tokens in the sequence. So this acts horizontally in this matrix. And we are going to go over each of those. The most important is the first one, which is the self-attention. And the output of the self-attention is going to be a matrix of the same size, D times N, and we are going to call it YM. And this is produced aggregating information across the sequence for each feature using a mechanism that is called attention. We will try to understand first what is attention. We will take the nth location in the sequence, which is going to be a vector. It's a vector representing, say, certain word in the sequence. We will take this location, certain word and the position of the word. Remember that both are aggregated. And the output is going to be computed as a weighted average of the vectors representing the other words in the sequence. Okay, nothing else. The intuition here is that if the word in position prime is very relevant to give meaning to the word in position N, then this thing is going to be high. And this is what is called the attention matrix. And it's a matrix N times N. This is a matrix N times N whose elements are normalized over columns to some one. Okay, so you can understand as probabilities. The higher it is, the most relevant is position word in position N prime to word in position N. But how is this matrix constructed? Well, first of all, in matrix notation, the whole operation over the sequence is this one. Okay, Ym, the output of the self-attention blocks, is X, the input sequence, times the matrix, the attention matrix. And this is a picture with the intuition or the graphical representation of what's being done. But what is the self-attention? Self-attention somehow needs to indicate us when our position is relevant to another. Yeah, this is the attention in position N. Each of these elements is telling you how relevant is N. Yeah. This is an example. So the color here, if you want, is like these words. I mean, the whiter, the more important. Let's say these words in these positions are more relevant for position N than others. But it's just an example, yeah. So one way of creating a naive way of creating an attention mechanism is by using the sequence itself, okay? Measuring how relevant is word in position N to word in position N prime, but computing the vector product, the dot product of the vector representing the word in position N and the vector representing the word in position N prime. And then this function, which is called softmax, is just normalizing this such that the numbers are between 0 and 1, and the sum of the numbers are 1. Okay, this is a naive way to do it. And this could work, but empirically, it is demonstrated that it's not the best way to do it. And the people give some intuition for why this is the case, but the only truth at the end is that it's better to do it in some other way, thanks to like the experiments have proved that. And the other way is applying the same function, softmax, which is this exponential of whatever is inside divided by the sum. Instead to the dot product of the sequence, first projects the sequence vector, in the token vector into a lower dimensional space through a matrix U, and then perform the dot product in this lower dimensional space. Okay, so U projects features to a space K, so the U matrices are K times D. And the intuition that they give you is that only some of the features of the input sequence need to be used to compute the similarity, not all of them, right? So if you are projecting them, this is capturing somehow a summary of the relevant features, and the similarity is computed between those two. And U is learned, yeah. That was the question, yeah, U is learned. But still, if you see here, the numerator is symmetric, and we don't want to be symmetric. We might want for a word to be very relevant to another word, but not the other way around. Okay. So the solution is very simple. We define two different matrices here, UK and UQ. And this quantity, Qn, which is this projection, and this other Kn, which is this other projection, both are learned. Those are called the query vector and the key vector. Query and key. And yeah, as you were mentioning, this is learned. The next thing is that there is only, what we have considered so far is only one possible attention mechanism, AM. But it would be useful to have, for a pair of points, to be similar, to have an attention mechanism across some dimension, but different across other dimensions. And as I said, this is just intuition that people give, but for the moment, there is no theory supporting these claims, but they work. Okay, so the solution to this is to compute, instead of just one, several attention mechanisms. There is going to be capital H attention matrices, and there is going to be capital H terms with attention that are summed. And here they introduce, well, here capital H is just the softmax between the query vector, the query vector for attention head H, and the key vector for attention head H, okay? And then they introduce here first the transformation of X, just because it works as well. Well, this is a representation, and this dot product here between X and H, this is just transforming, it's a linear transformation of X into a matrix of the same dimension. And it as well contains parameters that are learned, and this is called the value vector. Okay? So this is basically the attention mechanism. Something that is done, a little trick that is done is the inner dimension of this attention mechanism, the K, is chosen to be D divided by H. And this is done this way because if we do it this way, we ensure that the number of parameters are independent of the number of heads. If we choose a high number of heads, then the inner dimension of each of the heads is going to be small. So we keep the total amount of parameters. Well, I can show you quickly the codes. This is, I'm going to give you just a quick overview, but it's a bit more tricky than the previous ones. This is in modules. The only complexity here in the code is playing correctly with the dimension of the matrices that are involved, but it's nothing crazy. So here I have a class that defines the self-attention mechanism. So this will perform this transformation from matrix X in stage n-1 to matrix X of the same dimension in stage n, to matrix Y in stage n-1. Okay? For every of these PyTorch functions, you need to define the forward operation, which is the transformation that you are going to make, and then the derivatives are computed automatically by PyTorch using the automatic differentiation. Okay, so here E is the token embedding. What I'm doing is choosing the inner dimension of each head, which, as I told you, is E divided by H. I'm selecting the keys queries and creating keys queries and values. Keys queries and values are nothing else but linear transformations, as I told you, with the matrices U and B, UK, U and B. Okay. Here I'm extracting the submatrices corresponding to each of the heads, and I'm doing here I'm doing the vector product of the queries and the keys. This is just a normalization that is added. And here I'm doing the softmax transformation of this vector of this product of matrices. Once I have that, the output is nothing else but the dot product of the values that I computed before and this dot, which is the attention matrix, nothing else. And every detail that you see here is in order to correctly match the dimensions of the different matrices that are being multiplied. Nothing complex. It's very basic linear algebra. Okay. Best step of the transformers block, and is the most innovative block. This was introduced in a paper that was called "Attention is All You Need," and that was the one that bring transformers into play, and was super relevant and it's super highly cited. And is the next step, as I said, is a multi-layer perceptron across features. Now features are refined, each of them independently of the other features of the other vector representations in the sequence. So this just operates across features independent of everything. And this is very simple. It's just a multi-layer perceptron to apply to the vector of features at location n. Okay. So yn is the output vector in location n of the transformer block. So yn is containing information of other locations in the sequence already, and now it's transformed independently of the other locations into xn, applying a multi-layer perception, which is the most basic neural network. These parameters, theta, are length as well. And the relevant thing here is that these parameters are shared across every location. Okay, are the same across every location. Okay, so we have those two steps, but rather than stacking the multi-head attention, self-attention mechanism and the multi-layer perception directly, instead of performing one after the other, there are a couple of details more that help to stabilize training. These are residual connections and layer normalization. What is a residual connection? Well, let me give you the intuition. What we are doing now is mapping a sequence into another sequence. So somehow we are learning this function that maps a sequence into another sequence. Sometimes it's better to parameterize this instead of in this other way. We are going to learn the output sequence is going to be the input sequence plus a function that we call the residual connection. Okay. Why is this important? Because this is, instead of modeling the whole transformation, we are modeling the difference of representations of sequences rather than the full representations itself. And this works well when we believe that whatever is being learned is close to the identity and also helps stabilizing training. Okay, this is done in transformers and is used after both. We perform self-attention and when we add a residual connection. And then we perform multi-layer perceptron and we also add a residual connection. Okay. And the idea here is that we believe that each of these multi-layer perceptron and self-attention is going to be learning a mild, not a crazy one, but a mild nonlinear transformation of the sequence. And then there is layer normalization. It's another mechanism that helps with vanishing and exploding gradient problems. There are many choices, but ChatGPT, for instance, uses layer norm, in which the representation of each token is independently normalized in order to have mean zero and standard deviation. Okay. So each token, for each element of the vector representing token in position n, we will subtract the mean of all the elements in the token representing in the vector representing the token in position n, subtract the mean, divide by the standard deviation, and then we add a few parameters here, this beta and lambda, which are learned. Okay. And this essentially prevents the feature representation from blowing up in one. After every layer normalization, we are somehow, we are preventing this representation from taking very high and for very low values. Okay, so this is the transformer block. We have the input sequence, which is a matrix. Okay. First, we normalize the sequence through this mechanism, and we have the normalized version of this matrix. Then we apply the multi-head attention to this normalized version, plus we add the residual connection. Okay, so the output sequence is going to be the input sequence plus the head attention applied to this normalized sequence. Once again, we normalize the output of this, we apply the multi-layer perceptron and add a residual connection. And this is one block, one transformer. There are a lot of parameters here that have to be learned. And usually this transformer is applied many, many times. Okay, so let's go to where the transformer architecture is defined in the code. And this is in modules. Here I'm defining first, as I showed you before, the self-attention mechanism here. And here I'm defining the transformer block. Okay. I'm defining what is the layer normalization, what is the multi-layer perceptron. I'm using a multi-layer perceptron with a single hidden layer. And then the forward operation, which takes input into output. First, the self-attention mechanism is applied. I'm not normalizing here at the beginning. Then I normalize the output of the attention plus the residual connection. This is just regularization, is dropout regularization, not super relevant for the talk, but it works. It helps with the training and with the generalization. Then I'm applying a feed-forward neural network here, and I'm normalizing the output of the feed-forward neural network plus the residual connection. Okay, this is a transformer block. Okay, we are almost done. Okay, so we have the transformer block. This block is applied several times to the input sequence and generates a representation that has to be now introduced to the output layer. And the output layer will really depend on the task we are working on in particular. For instance, for classification, this output, this matrix, goes through a linear transformation that produces a vector over the set of classes. We have two classes, a vector of two elements, and this vector of two elements goes through a softmax operation, right, to normalize. Okay, it's taken the exponential of each of the elements is divided by the sum of exponential of all the elements. Okay, and this produces a set of probabilities over the classes. This is in transformers.py, and what we just see is very simple. Okay, let me show. Output. As you see, I apply something that is called self to props. Self to props is nothing else than a linear transformation that goes from the embedding dimension, the capital D, to the number of classes, which in my case is going to be 2. I send it through here, and then I just return the log the softmax function, apply over this. This log is for computational stability. That will for other tasks, the output layer is going to be different. For instance, for autoregressive models, the goal is to predict the next token in the sequence, given the previous tokens. So our goal is that the output to be a set of probabilities over the vocabulary, given this input. And for this, we need a couple of modifications. First of all, autoregressive predictions are expensive, and the reason is that if you want to generate a prediction, you first need to introduce the first token into the transformers, generate the output, then introduce again the input plus this output to generate the third position, and so on and so forth. So to generate a sequence of length n, this requires calling n times to the transformers, and this is very expensive. But there is a solution. Like we would like that if xn is the vector representation of a set of tokens, okay, and xn plus 1 is the vector representation of a set of these same tokens, xn plus another one, we would need this property to hold, okay? That the first n elements of this vector, or of this matrix, the first n columns of this matrix need to be equal to the other one. If we have this, we talk. But with the construction that we have, this is to ensure that the vector representation of token in position n just depends on the previous ones, okay? But with what we have until now, every token attends to every other. So this doesn't hold because the token in position n or in position j is affected by every other token. So this doesn't hold in general. The solution is very simple. We can mask the attention. We will set the attention matrix to be upper triangular. That means that for every n prime greater than n, the attention is going to be 0. That is, a word farther away in the sequence won't affect the representation of a word that precedes that one, okay? And with this way, how it works is we apply the masked transformer block m times to the whole sequence, and now we get a representation of every token in the sequence that just depends on the previous ones with this mask trick. Then to predict the next word, we take the representation at position n minus 1, which is going to be a vector that is learned, and we pass it through a linear layer and a softmax to get a distribution over the next token, over words in the vocabulary. Okay, this is this operation here, where these values of this linear transformation are also learned. Okay. Once we have this, we have a probability distribution of the tokens that are just affected by the previous tokens. Yeah, no, for the first one, you won't have troubles because that one is not going to be affected by nothing. So it's going to be a set of parameters that will define the representation of that element in the sequence. And in that case, the attention mechanism is doing nothing. It's like the identity because it's not affected by anything. With the mask transformers, the first position is not affected by nothing. The second is just affected by the first one. So. Not attended. Yeah, it's not attended. Yeah. That's something like, as I told, it's like this chunking thing is very easy, but this is a way to improve. Definitely. Okay, so once we have defined our architecture, has many parameters, we have the output layer and so on. The rest of the things I'm not going to talk about because we don't have enough time, but the loss function that we use depends on the task, but is almost always based on negative log likelihood plus a regularization term. Okay, so once we have in sentiment analysis, we have predictions of the next regularization term. And the training is done via stochastic gradient descent. The cool thing is that we don't need to worry about computing gradients because this is done for us by PyTorch. We just define the shape of a function and the gradients are automatically computed. And any variant of stochastic gradient descent can be used, such as Adam or RMS prop or wherever. And in the example, I'm using Adam. And as I said, this is done almost automatically. You can see how it is done in main.py, which is here. Here I'm defining the model, which is defined in another file in transformer.py with a set of parameters. Like the embedding size is the capital D, number of heads, so on and so forth. I'm defining the optimizer, which is going to be Adam. And in the optimization, what I do is I take a batch of data. Okay, this is the representation as a set of indexes of the batch of data. This is the label. I'm cropping the data in case it is very long. I'm just selecting the first max sex length characters. computing the loss of the output. This output is the output produced by the model, compute the loss. And this step is taking the gradient of this loss function with respect to the parameters and updating the parameters using Adam optimizer or stochastic gradient descent. So you, in a single epoch is not a lot of time here. It's like two minutes, more or less. But I'm running this in a server that we have here at CUNED with a GPU. So if you run it in your machine, it's going to be way more. Because in the local machine. And after the first epoch, the accuracy is already 66%. After 27 epochs, I trained the model and I saved it. And here I have a model after 27 epochs. The accuracy was 85%. That means that 85% of the test data is being correctly classified as positive or negative. And we can try. The first element here refers to negative, probability of being negative, and the second one to probability of being positive. And if I put this is the best, it's the type of here. It's because I did it last night. This is the best reading group I've ever attended, and it's going to tell you with very high probability or probability 1, this is possible. Okay, so it works. I would like to finish just with few thoughts. Well, I said this before, it's about the equivariance. Without the positional encoding, the transformer representation of a sequence is permutation equivariant. And this is not always desirable, but the solution is extremely simple. And this is one of the things that fascinates me a lot because it's so simple. And second is that transformers can be seen as a particular instance of what are called graph neural networks. It's a very exciting area of research, graph neural networks. Graph neural networks are neural networks that operate over graphs. Inputs are represented as graphs. The nice thing is that graph is a very, very extremely general representation of data and more natural than anything else. Also, text can be represented as graphs. And graph neural networks perform two types of operation. There is something that is called message passing, in which every node receives messages from their neighbors and aggregate those messages. And the neighbors are defined by the structure of the graph, by the connectivity of the graph. And then there is another stage, which is node update, in which every node, the features of every node, are updated independently of every node. And this is essentially what transformers are doing. But as attention depends on every other word, transformers can be associated with graph neural networks that are fully connected. Every node is a word, and every node is connected to every other node. Every word is connected to every other. And in this the first step would be the self-attention mechanism, in which messages are exchanged by every word in the sequence. And then the second stage, every word representation is updated. There is something that are called a sparse attention mechanism, in which attention is not applied, does not depend in every other word in a sequence, but just in a few. It's called a sparse attention. And this corresponds to graph neural networks that are not fully connected, but has sparse connectivity. Okay. And maybe associating transformers to graph neural network is a way to start understanding them. Well, and a cool thing about transformers is that the connectivity of the graph can change from layer to layer, while in graph neural networks it's always the same. Well, second is that I just explained you what is the transformers block, and this block is used within many other architectures. There is something that is called encoder-decoder architecture, in which the goal is to solve sequence-to-sequence tasks. There is encoder only, in which the goal is to learn useful representations for downstream tasks, and these are BERTs. BERTs is the example of this, or decoder only for text generation. Okay, and this is what GPT does. But this is going to be the topic of the next week's session. Go more into the detail of other architectures that use transformers. No, the model is the building block of every of these ones. So encoder has like two separate neural networks. Each of them is composed by several transformer blocks, and those interact to work with encoding the data. Yeah, I mean, what I've described, like the transformer blocks in, for instance, in the decoder that was presented in Attention is All You Need, is present both in here and in here, in the encoder and the decoder. Essentially, in this one, the encoder takes as an input the phrase in Spanish through the application of several transformers blocks, learns a representation, a vector representation of this one, and this vector representation is given to the decoder plus the input representation, which is the phrase in Galician, and that is used to produce the output. It's the first word of the phrase in Galician, and it's used to produce the second word of the phrase in Galician, so on and so forth. But both of them use the transformers. Well, I mean, for instance, in this paper, the encoder is already applying in sequence several transformers blocks. So if you put many encoders, it's like putting way more transformers blocks. And how many of them you put, these are all hyperparameters that you need either to choose based on your experience or to try to validation data. But there is not an answer of what would be the effect. Yes, I mean, I don't know is the answer. Like I don't know what's going on inside. It's very hard. It's easier to understand in graphs, for instance. Like if a graph is not fully connected, if it is not fully connected, after the first operation, each node is talking to the first neighbors. But if you do two operations, each node is talking not to the first ones, but to the second. But here, the attention mechanism is so general that you cannot know what is going on. Yeah, there are attempts to visualize what is happening, but it's very hard. Like it's impossible nowadays to say something. And yeah, these are the readings that appear in the website, and maybe that. Definitely having more than one is different to having one. Like, but just based on what it has been seen empirically, I don't think there are, like, for instance, in multi-layer perceptrons and in these deep networks, there are universality theorems that tell you that a single layer neural network with a arbitrary number of nodes can approximate any continuous function, or a neural network with an arbitrary number of layers can approximate any continuous function. I don't think so. For the moment, I mean, it's such a complex architecture that understanding things there is hard. You introduce regularization, like I believe that in GPT there is a lot of dropout layers. Dropout layers are layers in which some randomly chosen. But this is trial and error, and is in fact is what is giving value to these companies. Their own cooking of these models is what is giving value to them. Like complex, and there is a lot of trial and error work. It's not easy to find a good model. If it was very easy, like everybody would have one. massive. Parameters in one block can be different from the others in the next block, but they are the same for the sequence. So this theta does not depend on n. So for position n, I and j, this for position I and j, these are the same ones. It's the same. So you are learning a representation, fine-tuning a representation, or refining a representation that does not depend on the position, in the sequence. That allows, so the masking thing allows to just in a single pass over the transformers, the transformer architecture, just a single pass to make predictions of not only the second word given the first one, but also the third one given the first two, the third one, just a single pass. Like this will give us a vector of probabilities for the first one, the second one, the third one, the fourth one, for all the sequence, just with a single pass. And this has the property that these probabilities computed for the n word just depends on the probabilities of the first n minus one. So it's a computational, the masking mechanism is just a computational trick to avoid having to call the transformers block n times for a sequence of length n, and instead do it in just one single code. And this has advantages because this architecture is fully parallelizable, while in recurrent neural networks, in order to compute the parameters corresponding to the nth hidden unit, you need to have computed before the parameters of the n minus one hidden unit. And here it is not the case. So you can parameterize. Okay. Yeah, because these are subwords. Like you can create a word combining two subwords, right? So with these subwords are like, imagine 3 letters, and there are many words that has 3 letters in common. So just by combining these elements of this set of 50,000 subwords, you can create every word in English. Yes. I would say, but I am not 100% sure that GPT, like this data is about English subwords. But yes, definitely. I mean, for sure, like I mean, maybe I don't know how they construct it, but maybe they divide the whole dictionary into subwords and they take the 50,000 more common ones. But I'm not 100% sure. I want to see if there is something in the chat. If there is someone in the chat that wants to ask, can just unmute and ask.
I am curious about the way you would use sparse attention, what you mentioned at the end. Would you use, for instance, like a dependency parser or something like that to establish which words are connected?
An option, or the other option is to force the number of zeros that you will put in the attention matrix to just at most be affected by a given number of words and learn those locations. But I don't know exactly how a sparse attention is done, but it's something that has been studied. Yeah.
Okay, thanks.
More questions? Thank you for coming. Yeah.